Hi everybody, welcome back to this course on Internet Technologies. I'm Vardan and today we'll be studying about routing protocols like OSPF, RIP and BGP. So let's start by understanding what an autonomous system or AS is. An autonomous system is a collection of routers and networks managed by a single organization like an ISP, university or a company. All routers inside an AS follow a common routing policy. Now, within an AS, routers need to communicate with each other in order to exchange routing information. This is handled by interior routing protocols or IGPs. In, Examples include RIP and OSPF. On the other hand, when traffic needs to move between different autonomous systems, like from one ISP to another, it's managed by exterior routing protocols or EGPs. The most important of these is BGP, the protocol that literally keeps the global internet routing systems running. So, routing happens at two levels: inside an autonomous system using IGPs and between autonomous systems using EGPs. The first routing protocol we'll discuss is RIP or Routing Information Protocol. It's an interior routing protocol that uses a technique called distance vector routing. Here's how it works. Each router maintains a table listing all possible destination it knows along with the distance to them. In RIP, the distance is measured in the number of hops or routers between the source and the destination. The maximum number of hops allowed is 15. A distance of 16 is considered unreachable. So RIP relies on Bellman-Ford algorithm, and each router periodically sends its entire routing table to its direct neighbors. These neighbors update their own tables based on the information received, and this approach is simple, lightweight, and works well in small networks. So let's see RIP in action. Every router periodically shares its routing table with its directly connected neighbors. If a router doesn't receive an update from a neighbor within a certain time, it assumes that the link has gone down. It removes it from its table and informs others. When a router receives an update table from a neighbor, it checks the distance values. For example, if router A thinks the distance to network X is 5 hops and a neighbor says, "Hey, for me it's only 3 hops," the router A will update its table to reflect new value of 3 plus 1 equal 4 hops. This process happens continuously, keeping each router's view of the network up to date as long as the network isn't too big. So while RIP is simple and easy to implement, it has several drawbacks, especially in large or complex networks. First, it suffers from slow convergence. When a link fails, it takes time for all routers to update their tables and settle on a consistent view of the network. Second, due to asynchronous updates, it's prone to routing loops where data can circulate endlessly between routers. Also, RIP uses a lot of bandwidth by regularly exchanging entire routing tables even when there's no change. Lastly, and most critically, it has a built-in limit of 15 hops. Any destination beyond that is considered unreachable, which makes RIP unsuitable for large enterprise or internet service provider level networks. And these limitations are why newer and more sophisticated protocols like OSPF and BGP exist. Next, let's talk about OSPF, that is Open Shortest Path First. It's a widely used interior routing protocol that operates using a technique called link state routing. Unlike RIP, where routers only know about their neighbors, in OSPF, every router maintains a complete map of the network's entire topology. It uses Dijkstra algorithm to calculate the shortest, or rather the best path to every destination. What's unique about OSPF is that instead of hop count, each link has a configurable cost value, which can reflect bandwidth, delay, or any other metric the network admin chooses. This allows for far more optimized routing decision, especially in complex and multi-link environments. Now, how does OSPF actually work? Every router in an OSPF based network independently runs Dijkstra algorithm on its personal copy of the network's topology map. Using this, it calculates the best path to every other router and network. Even though it knows the full topology, each router's routing table only needs to store the next hop for each destination, which keeps the routing process efficient and scalable. This approach makes OSPF fast to converge and highly reliable for large and complex networks. To keep its network map consistent, OSPF uses two important mechanisms: hello packets and link state advertisements or LSAs. Hello packets are sent every 10 seconds to neighboring routers, and if a neighbor fails to respond within 40 seconds, it's considered down, and the topology is updated. LSAs are how routers share topology information. Whenever a network change occurs, like a link going down, the affected router generates an LSA which is flooded throughout the autonomous system. And routers also periodically send LSAs without changes to confirm stability. And this mechanism ensures all routers have a synchronized and up to date view of the network. Now, OSPF uses several specialized packet types to manage routing information efficiently. Hello packets establish and maintain neighbor relationships. Database description exchange summaries of topology databases between routers. Link state requests are request specific LSA entries for neighbors. Link state update share new or updated LSAs. Link state acknowledgement confirms receipt of LSAs. Additionally, OSPF optionally supports authentication, which ensures routers only accept routing information from trusted sources, adding a layer of security to the protocol. While OSPF works brilliantly inside an autonomous system, it wasn't designed for routing between different autonomous systems. Between two autonomous systems, the full network topology is unknown, route changes are frequent, and WAN links and ISP level routing can't afford constant topology floods like OSPF. To handle this complexity, the internet uses BGP, that is Border Gateway Protocol. That's the global standard for routing between two autonomous systems. So let's get to know about BGP. It's the protocol that allows routers from different autonomous systems to exchange routing information. BGP runs over reliable TCP connections and uses four primary message types. Open establishes a session between routers. Update announces new routes or withdraws unavailable ones. Keep alive is periodically sent to maintain connection health. Notification are signal errors and they terminate the connection if necessary. Thanks to its flexibility, BGP is what keeps the global internet's complex routing system running smoothly. So, with that, we've come to the end of this lesson. In the next lesson, we'll be learning about IP version 6. And thank you for joining in, and I'll see you next time.